Okay, DC motors. I was going to, can't do two things at once. I was going to add AC motors as part of this lecture. It's still possible that over the break I'll decide to do an extra lecture on AC motors, but for now we're just going to do DC motors. There was enough to talk about with DC motors that I just really beefed it up, and yeah, I think it'll be fun. So 4.3, DC motors. They're commonly used in mechanical engineering designs as an actuator. So it's probably the most common actuator, well, motors at least, are the most common actuators. DC motors are one type that show up. So products such as pumps, fans, conveyors, and robots use DC motors to convert electrical energy to mechanical rotational energy. DC motors first emerged in the mid-19th century as the first device to produce useful mechanical work from electrical power. So this is the key thing for us, right? We got this electronics. We want to be able to do mechanical work with the electrical power. One of the fathers of the DC motor, the Benedictine priest Ányos Jedlik, invented the key facets of the motor: the stator, the rotor, and the commutator. Roughly speaking, for a typical brushed DC motor, current flowing through the wire windings of the stator produces a magnetic field that turns the rotor, which has windings of its own. The commutator mechanically switches the direction of current flow through the windings to yield continuous electromagnetic torque. So this is something we're going to dig into a little bit deeper, but it's kind of cool that one of the well, I think it's a sort of contested fact that this Benedictine priest is the guy who invented these things, but at least so he's Hungarian. At least the Hungarians really think that he was the one who invented the motor. So I think it stands. At a Benedictine school, we can say that is the case, right? So we will begin our study of DC motors with a review of a key physical phenomenon: the mechanical force on a particle, a charged particle moving in a magnetic field. So this is going to be going back to your physics 172 days, or your physics 2, or your physics 3, depending on where you took it, days, where you've got charges in magnetic fields. So consider a charged particle moving through a background magnetic field. The Lorentz force is the mechanical force on the particle, which depends on the velocity of the particle, the background magnetic field, and the background electric field. So this is the sort of physical phenomenon that's harnessed to make mechanical, or I guess to convert electrical power into mechanical power. Okay, so this is what it all kind of comes back to. Charge flowing through a straight, stationary wire with current I in a uniform background magnetic field B is subject to the cumulative effect of the Lorentz force on each charge. So if that's true for one charge, you can put a whole bunch of them in a wire, all moving in the same direction, and they're all going to get forces in the same direction resulting from that. So as long as you have a uniform magnetic field, they'll all be in the same direction. So let the straight wire's length and orientation in the B field be described by the vector L, which should be chosen to be in the direction of positive current flow. It can be shown that the resultant force on the wire is I, so the current, times the cross product of L and B, the background magnetic field. So I'm confident that you guys have seen this equation before in your physics class, or at least a version of it. It might have been a scalar version of it, but it was definitely something like this equation. So 4-2, we're going to draw it. Okay, so let's draw a well, let's just draw a magnetic field. We're going to have the field lines going uniformly horizontal. So we'll have them all going this way. This is our B field. And we're going to put a wire through it. I mean, this is a three-dimensional thing that's happening here, right? But I'm going to do it in the plane so that we can more easily see what's going on. So I'm going to put a wire in the field, like right here. We're just going to see a cross-section of the wire. I'll make it a little bit bigger. A cross-section of the wire. So it's going into the board, right? So we've got, there are different ways of drawing vectors into and out of the board. You may have seen this version before. We put the dot, which is supposed to be the arrow tip, which is still ambiguous, but those are the arrow tip. When you see the arrow tip, typically it means that it's coming out at you. And you can also see the arrow tail. We'll do another one with the tail as well. And that's the X that you see in it. So if you've got this wire and it's got current flowing, so the direction that it's going to be flowing is going to be out of the board at us. We want to know what direction the force is going to be on this wire, okay? So L, I guess, is coming out of the board, so we could draw L like that. So how do we determine the orientation from a cross product again? Do you guys remember? Right-hand rule. Okay, so the way that we like to use it is your, what is this, index finger? Is that what they call it? Pointer finger? I feel like that's like the baby name for it. It's your pointer finger, yeah. Your index finger in the direction of the first vector. So for us, that is going to be coming out. So L is the first vector in the cross product, right? So L coming out of the board. So I'm going to do it for you guys. So out of the board, okay? And then we've got the B field, which is going for you guys. So you set your middle finger. Your middle finger points in the direction of the second vector. So that one is, so I point it out, and then I have to point this way, and not break my wrist trying to do that. And then if I thumbs up, that's the direction of the cross product vector, right? So that means that we have a force down. Cool. Let's do the other direction too, just for completeness. X. So that means we've got the current flowing into the board this time, right? So we have our finger. We have to point it toward the board, this way. I have really nice elbow pads here. Into the board, and then we point our middle finger in the direction of the field, so that way. Did I do that right? Into the board. No. That way? Oh yeah, wait, I gotta do it this way for you guys, that's right. Okay, this way. So then, so into the board and that way, and then my thumb is pointing up right? So that makes more sense. Very good. So our force is going to be up. Cool. So that is how we're going to make motors work, essentially, DC motors work. So let's pick up the thread again. With a curved wire, then, we could take infinitesimal sections, dl, and integrate along the wire's path, as shown here. So they don't have to be straight wires. Also, I'll mention that these equations assume that the wire is stationary in the field. Our wires are going to start moving, which does add another effect, but the Lorentz force is still present. It's just there's another effect in play as well. We can effectively ignore for the purposes of our analysis here. But it is good to remember that, when the wire starts moving, this equation is not perfectly true. Okay. DC motors take advantage of this electromechanical phenomenon by driving current through cleverly arranged wires to generate torque on a shaft. Okay, so we're going to have this background uniform field. We're going to drive current through the wires that are in it, and then we're going to use that force, Lorentz force, that accumulates on the wires to drive mechanical rotation. So let's consider the first type of DC motors. We're going to consider several different types today. This is the first type. Permanent magnet DC motors. In order to take advantage of the Lorentz force, first a uniform background magnetic B field is required. Some DC motors called permanent magnet DC motors, sometimes abbreviated PMDC motors, generate this field with two stationary permanent magnets arranged as shown in figure 4.3. So down here. So we're going to put, in order to generate that field, we're going to put two magnets here. And they might not be simply rectangles. They might have some curvature to them. But they should, the key is that they're going to generate these magnetic field lines that we want, uniform field lines. Just like we had in our previous diagram that just appeared from nowhere, we'll have to actually make them with two permanent magnets, so say north and south. So they can be like neodymium magnets, for instance. And small DC motors are often permanent magnet DC motors. They can be relatively inexpensive and powerful for the compact versions. The trouble when you get to bigger ones is creating a uniform field through a larger and larger region. The fields, the permanent magnets only have a certain distance of action where they can create a uniform field. So you need more compact motors typically in this case. And actually the one that we're going to do a lot of analysis on that's in the lab and do a lot of modeling on is a permanent magnet DC motor. Okay, so the magnets are affixed to a stationary part of the motor called the stator. So stationary in the sense that oftentimes our motor is going to be connected to something that is moving, but it's the chassis, right? It's something that it's relatively stationary. And we call that part of the motor the stator, okay? Stationary stator. Now consider a rigidly supported wire with current I passing through the field such that much of its length is perpendicular to the magnetic field. So that's the arrangement that we had up here, right? We had the wire going perpendicular to the magnetic field. Okay. So we want a good portion of this wire, in this case, to have this perpendicular action, or orientation, I should say. Consider the resultant forces on these perpendicular sections of wire for different wire configurations, as illustrated in Figure 4.3. So now what we did before is we were like, okay, we just put two separate straight wires in. But let's imagine that we're going to put one wire in that's going to go into the into the board and then back out of the board. So one loop, right? It goes in the board and then back out. And if that was the case, so say we had it oriented like this, where we have into the board, and then it goes down, and you could like put like dashed lines, like and then it comes back out of the board. That wasn't my best circle. Live your best circle is what I always say. Okay. So now we're going to have this wire extend in there and then come back out, right? So imagine that a good portion of it is running perpendicular to the field, which is to say into the board and then out of the board. Now, if we have this rigidly suspended, so it's like it's wire, but maybe it's like a really stiff wire, or more realistically, it's got like some sort of steel structure that's holding the wire, like a copper wire, in place. Then this this loop is going to be subject to the same forces we drew before, right? So we said that this force was going down, right? And this force was going up. So that's pretty cool, right? Because what we've done is we've created a torque on this rigidly suspended loop in the field. Effectively, we've created a torque in this direction, right? Great. So we've got a couple, right? That's what in statics or dynamics we call a force couple, right? So that gives us a torque, and we could turn something. Like if we connected up this rigidly suspended wire to something mechanical, it would turn something. That's the action that we're looking for, right? But let's look at another orientation of this. So let's look at one that's I guess perfectly vertical. When it's in that orientation, then the force on this one's still up, and the force on this one is still down. Do you have any torque? No, because they're on the same line of action, right? So there's no torque in this configuration. And then in between those two, if you have like a 45-degree angle, you have torque, but less torque than you had. This is like the optimal when it's horizontal, and then when it's at an angle, you get some torque, and then it keeps going. And then if you were to think about what happens if you continue to rotate this, like let's do one of those like 45-degree angle situations, say like this configuration, where you've got force up here, and you've got force down here. You have torque, but now the torque's going in the other way, right? Now torque's going this way. So you can create torque, but like it kind of diminishes as you go to the top, and then it actually changes direction, which is usually not what you want, right? You don't really want motors that just go back and forth, right? That's not really what you're trying to do. So there are some issues with turning this thing directly into a motor. We've got the right idea, though. We've got the ability to create torque from running current through a wire in a magnetic field, but we still have some issues with it. Okay. So we have torque. Note that we can wind this wire, which we call the armature. So this is one of those key words that you'll hear in discussions of motors. The armature, multiple times around the loop to increase the torque. So you run it through once, and you get a certain amount of torque. You run it through twice, you get more torque, etc. So you just can keep adding torque the more turns that you go around. And that's usually what we do. The rotating bit of the motor that supports the armature is called the rotor. Okay, so that usually includes the shaft as well. So the part that you want to have turn is called the rotor. And the armature is the thing that helps the rotor interact with the stator and do that turning. Okay. Now, the only trouble is, if we connect our armature up to a circuit, which is usually located alongside the stator, i.e. not rotating. So our circuit's not going to be like on the shaft, right? The power circuit's going to come from like the housing outside of the motor connected to the stator. It's not going to be rotating, but we want our armature to be rotating on the stator. So this is kind of an issue. The wire will just wrap around itself, which is not #winning, right? That's not what you want. You don't want to like turn on your motor and then have the wires that connect up to it power just go and just wrap themselves up until they rip out or something. But we're tricky AF, so let's consider just cutting that wire and rigidly connecting it to a disc called a commutator with two conductive regions, one for each terminal of the armature. So let's I could draw it on here. I'll draw it as like this is where it would exist. So the commutator would go right here. But let's pull it out because it's a little bit messy in there. Let's draw the commutator. Very simply, we could just think of this as being a ring of metal that has some sort of support inside of it with two regions of conductive contact. Split, let's just schematically draw it as just being split in half. So say this is like conductive, like copper, and this is copper over here, but there's some insulator in between. In reality, we don't make these entire things out of copper, because that would just be expensive. We don't need it to conduct along like the whole thing, but we could think of it schematically this way. So this side would be like the plus side, and this side would be the minus side. And the armature, this thing that the wire loop that we have in there, can connect up to this rigidly. So I'll show us sort of a 3D view of it, where we've got the armature going out into the field, and then connecting up to this disc. Okay, and this disc, this commutator, is going to have some sort of support, some sort of mechanical support that holds it in place, and it's going to rotate with the armature. So the armature and the commutator will rotate together, and then we're going to put what are called brushes on here. And brushes are effectively little conductive chunks of usually carbon that conduct electricity, but also allow the commutator to slide relative to them. So they are in contact. There's usually a spring here that's pushing these into contact with the commutator. And it's carbon, which actually is it's not super high friction, relatively low friction. And it allows current to flow from the circuit's power. So you've got like a source here that you connect up to the brushes. This is your driving circuit. Obviously, it might be more complicated than just like a source. And then what happens is, let's think about what happens. So you turn this on, and it flows current through the loop this way, right? Great. And then once this commutator turns to the point where it flips, the plus and minus are going to flip when it gets over to the other side, right? And current's going to start flowing. Effectively, instead of from plus to minus, it's going to start flowing from minus to plus, right? That it corresponds with moving from this side of the region where you have torque in one direction to the other side. We have torque in the other direction. So effectively, you can have the torque action continuous in one direction. It still gets smaller and smaller as you get up to the top, and then increases again, which is unfortunate. But there is a way that we can get around that. So we just have to be more clever again. But at least we've solved a couple things. We've solved this like wire wrapping problem, okay, and we've also solved this issue of the torque switching directions. We can keep the torque in one direction, and we can allow there to be this electrical contact without having wires that are going to wrap around each other. So, good. So the commutator will rotate with the armature, but it provides smooth contacts along the perimeter of the disc. We can then connect the driving circuit to these contacts via brushes. So these are the conductive blocks that press against the commutator on opposite sides such that they remain in contact, conducting current, yet allowing the commutator to slide easily. So those brushes are going to wear out. So like the carbon that is in contact, the brushes, they wear out over time. It creates a lot of carbon, just dust that's inside the motor, and that means you have to service them, clean it out, and then the brushes eventually are going to wear out. So one way to mitigate that is to have them be spring-loaded so that it keeps feeding more and more brush in, but eventually they run out and you have to replace them, right? So that's one of the biggest downsides of having a DC motor, is you have to replace the brushes and they need to be serviced and cleaned. Good. is there a way to overcome the limitation of torque variation with different armature angles? So we've got, this like when it's vertical, it's not really providing any torque. Yes. So there are several different armature windings. So if there are several different armature windings at different angles, and correspondingly, the commutator is split into several conductive contact pairs, one for each armature winding, a relatively continuous torque results. So instead of just having two sides to your commutator and only one armature, we could do, for instance, you could split this into 4 regions where you have like the opposing sections of plus and minus, and then you have another armature winding. So this is just an example of another one. And it gives, so when one is in the correct, or in the best orientation for torque, the other one's not. You need to have at least 2. But usually we end up having like, I don't know, maybe, yeah, I mean, it depends. The size kind of limits too. So if you have a really small, compact one, you can't get too many. But I mean, I would say I've seen a typical one would probably have to be like 12. Yeah, like in that range. But so it runs more smoothly the more you have. So real permanent magnet DC motors use this technique. Okay, so that's permanent magnet DC motors. Okay. Now let's talk about wound stator DC motors. They operate very similarly to PMDC motors, but generate their background field with 2 stationary coils in place of the permanent magnets above. So we had those 2 permanent magnets, but instead of doing that, we're going to use electromagnets to provide that background field. These electromagnets require a current of their own, which is usually provided through the same circuitry that supplies the armature current. So DC motors typically only have 2 terminals. So it's not like you have terminals for the stator windings separately from the armature windings. Usually you only have 2 terminals, so you don't power them separately. So 3 common configurations of the electrical connection of these are shown in figure 4. These define the following 3 DC motor types. So I'll draw them as we talk about them. So first is the shunt DC motor type. So I'm going to draw, like, here's the mechanical part of the motor. So we've got our like rotor in here, and then I'm gonna put we're gonna put coils on each side here instead of those permanent magnets. And we're also actually, I'm not going to do that because that's going to be confusing, because that was the other. Okay, so I'm going to instead do, here are the leads for the armature winding, okay? And then I'm going to draw over here, we're going to have the coil. It's actually going to be on both sides, but I'm just going to represent it on one side for now. What we're going to do is we're going to just connect them in parallel. So the background field is being generated with this with the same voltage from your source. So call that just Vs, and this is ground. So this would be called the shunt configuration. So you just connect the coils, the stator coil and the armature coils in parallel. And a lot of wound stator DC motors are of this configuration. The most common type, their speeds can be easily controlled without feedback, but they have very low starting torque. So one of the issues is getting them going. Okay, so when you've got a big load that you've got to get started, sometimes you don't have enough power to drive that when you have it connected this way. The next one is to just do series instead. So you've got your armature again, and your leads coming off the armature. And instead of connecting this thing in parallel to the source, what you're going to do is you're going to go through your coil, your stator coil, and then you're going to go back up and connect to your source and connect this to ground. So that one is the series motor. And the series motor is has the distinct advantage that it has great starting torque. Okay, you get a lot of low-end torque, but it is harder to do speed control without feedback. When I mean feedback is measuring what the shaft velocity is. You can always do that, and then you can control your motor that way. But a shunt motor actually can be pretty easily controlled, speed controlled without that. And a series one requires usually some feedback if you're going to do that. Now, there's also the hybrid, or it's called the compound DC motor. And this will be the last thing we cover. And once again, we've got our armature coil, and we've got, what we have this time is, see if I can draw this without screwing it up. We've got a series one that goes up. I don't want to cross my wires here. Printed out these configurations so I didn't do this. Okay, yeah, it goes up. Maybe not quite as far as I drew it. And then we've got another one that is the parallel coil that connects up to here and then goes up to the S. So this is the compound, and this one can blend some of the advantages and disadvantages of each, so you can get some better starting torque from these, but the speed control is a sort of trade-off there. So you get some of the advantages of both. You can get kind of hybrid performance out of these. If you're looking for something that has great starting torque, you're probably going to want to do series. If you want something that has great speed control and you don't care about starting torque, then shunt. Something about series that you should be careful with is you should always have a load on the series motor when you power it. If you power it without a load, you can cause damage to the motor. So it's kind of an issue. Okay, so I'll talk more about brushless DC motors after the break. We'll come back to this. Yeah. So have a good weekend studying, and I'll see you guys on Monday for the exam. No, DC motors will not be on the test. Yes.